An isomer is a substance that has the same chemical formula as another substance but differs in its structure. So when we look at isomers, they'll have the same chemical formula but different structural formula. Or they'll have the same number and type of atoms, but their arrangement will be different. Okay, so if we wanted to draw and name all the isomers of pentane, the first thing we would need to do is figure out what the formula for pentane is. Okay, so pent means 5, so that means our N number is 5. ANE tells us it's an alkane, and we know the formula is CnH2n plus 2, so 2 times 5 is 10 plus 2 is 12. So the chemical formula for all of the isomers of pentane are C5H12, or there are 5 carbons and 12 hydrogens in every isotope. So our first isotope is going to be 5 carbons in a row. And again, we know that the hydrogens are in along here. We're just going to draw the skeletal structure and leave the hydrogens out. There aren't any branches on this, so the name for this isomer is just pentane. But what we can do is get rid of one of the carbons off the parent and make it a branch. We'll still have 5 carbons and 12 hydrogens, but the arrangement will be different. So if we had 5 carbons, now we're going to make an isomer that has only 4 carbons in its parent chain. Now we need one more carbon, so we're going to need to put another carbon somewhere. We can't put it here because that would just extend the parent, and we can't put it here because that would just extend the parent. But we could put it here. And again, we've got all the hydrogens that would be bonded to the carbon atoms to give them 4 bonds. We're just going to leave those out and write it as a skeletal structure. And now we're going to have a methyl group coming off of the parent at the second carbon. So our name would be 2-methyl-butane. Now, we can't put the methyl group here because then we'd start counting from this side, because remember when we count with branches, we always start counting from the side closest to the first branch, and that would still give us 2-methyl-butane. So the next thing we're going to do is get rid of another carbon off of the parent, and that's going to make our parent a 3-carbon chain. We need 2 more carbons so that it's an isomer of pentane. We can't put a branch here, and we can't put a branch here, but we could put one here and one here. We have 1, 2, 3, 4, 5 carbons, that works. And we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens, so that would be an isomer of pentane. Now we've got a methyl group here coming off of the second carbon, and we've got a methyl group here coming off of the second carbon. So our name would be 2,2-dimethyl-propane. Propane means we've got 3 carbons in our parent, 2 methyl groups, they each have 1 carbon, and they're coming off of the second carbon. So all 3 of these are isomers of pentane. They have the same chemical formula, but different structural formulas. So now we're going to talk about a different kind of organic compound, which is called an alkene. And notice that the difference in the name is instead of being ending with ANE, it's ending with ENE. So when we look at alkenes, they're considered to be unsaturated hydrocarbons. And the reason for that is they're going to have double bonds between carbon atoms in the parent chain. In order for us to have a double bond, we're going to need to remove 2 hydrogens to make that double bond. So our formula for alkenes is CnH2n. So let's talk about how we name alkenes. Okay, alkenes are named according to where the double bond is. So when we find our parent chain, it needs to contain the double bond, And we're always going to start numbering from the side closest to the first double bond. The parent compound is named from the longest continuous chain that contains that double bond. So in other words, the double bond can't be on one of the branches. And our suffix for alkenes is going to be ENE, just like when we look at the name of the group, it's called an alkene. Our prefixes are going to remain the same. So let's say that we've got 3-hexene. The ending tells us we're going to have a double bond somewhere along the parent chain. Hex tells us that there are 6 carbons in the parent chain, and this 3 is going to tell us where that double bond is located along the hydrocarbon chain. So if we wanted to draw this, the first thing we do is our chemical formula. So C6, okay, is going to be our N number. H12, because our general formula for alkenes is CnH2n. So we'll draw our parent, 1, 2, 3, 4, 5, 6. Our double bond is going to be after the third carbon, so 1, 2, 3. There's our double bond. And now we want to fill in our hydrogens. So we've got 1, 2, 3, 4, 5. This carbon's only going to have 1 hydrogen because it already had 3 bonds. This one's only going to have 1 hydrogen because it had 3 bonds. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So our structural formula matches up with our chemical formula. Okay, so let's say we've got 2-methyl propene. We want to start from the back of the name and go forward. So the ENE tells us we've got a double bond somewhere along the parent chain. Prop tells us we're going to have 3 carbons in the parent. So we'll start there. 1, 2, 3. Methyl tells us we're going to have a branch, and the branch is going to contain 1 carbon, and it's off of the second carbon of the parent. So our second carbon is going to have a methyl group. Now, it doesn't tell us where that double bond is because it doesn't matter for this particular compound, because we could put it here and it would be off the first carbon, or we could put it here and we just count in the other direction, it would be off the first carbon. Up here with this example, it had to tell us where the double bond was because it could have been anywhere along that chain and it would have given us a different structural formula. So when we look at this formula, we're going to have 1, 2, 3, 4 carbons, and we're going to have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. Remember again, this carbon can only have 4 bonds, and it already has 1, 2, 3, 4 bonds, so there's going to be no hydrogen coming off of that carbon. So let's look at another example. Let's say we've got 4-propyl 4-octene. And we'll just break the whole name down. We know we've got a double bond. We know that our parent's going to have 8 carbons. So 1, 2, 3, 4, 5, 6, 7, 8. Now that double bond can be anywhere along that chain, so this number is telling us where the double bond is. So 1, 2, 3, 4. Double bond is going to be after the 4th carbon. We've got a chain or a branch coming off of the chain. Prop means 3, so we're going to have a 3-carbon branch, and this 4 tells us where that branch is going to be. So 1, 2, 3 off the 4th carbon, we're going to have a 1, 2, 3 carbon branch. And again, we could fill in the hydrogens there. We're going to leave it as a skeletal structure just to shorthand it. Now we've got alkynes. So there's alkanes, which are saturated hydrocarbons with only single bonds. We've got alkenes that have a double bond somewhere along the parent chain. And now we've got alkynes. Alkynes are also considered saturated hydrocarbons. But this time they're going to have a triple bond found somewhere along their parent chain in that hydrocarbon. And when we go to name it, or write the chemical formula for it, it's going to be CnH2n minus 2. And the reason for that is if we're adding a bond between two carbons, we're going to have to remove two hydrogens to do that. And when we name it, just like we did for alkanes and alkenes, our suffix is going to be YNE, which matches up with the group name. Now, the next thing we want to deal with is what are called cyclic hydrocarbons, or sometimes they're referred to as cycloalkanes. And basically, we're looking at organic compounds, in this case alkanes, that come in cycles or rings. And when we look at these, they're going to end CnH2n. So let's look at an example. Okay, let's say that we've got cyclohexane. Single bonds, 6 carbons, and this time those 6 carbons are going to be in a ring. So we've got 1, 2, 3, 4, 5, 6 carbons in a ring. Each carbon right now has 2 bonds, so we would need to put 2 hydrogens here, 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 and here, and that would give us C6H12 for our formula. Now, with cycloalkanes, we can have branches. So if we have cyclohexane, we can have an ethyl group coming off of it. And since there's only one branch coming off of our ring, it doesn't matter where we put it. Kind of traditionally, we're going to start and go around clockwise. So we'll put an ethyl group, which contains 2 carbons, coming off of that cyclohexane. So let's look at the last one. Okay, we've got cyclohexane again. So 1, 2, 3, 4, 5, 6. There's our cyclo. We've got branches. They're methyl branches. There are 2 of them. Well, now there can be several places where those branches can come off of, and we need to know relative where they are. So we're going to have a methyl group coming off of the first carbon, so we'll put that there. And then we're going to have a methyl group coming off of the third carbon. So if this is the first, this would be the second, this would be the third. Okay, and again, we would fill that in with hydrogen so that each carbon has 4 bonds, but we're going to leave it as the skeletal structure. The last thing we're going to talk about is the structural formulas for halogen derivatives. And if we remember, halogens are structures that, or elements that are found in group 7 on the periodic table. So fluorine, chlorine, bromine, iodine. And they're going to function a lot like hydrogens in our compounds. So if we have 2 bromopropane, we would have single bonds, 3 carbons. We would have a bromine coming off of the second carbon. So the second carbon would have a bromine. Now, we're not going to put any hydrogens on there because we know that halogens can only form 1 bond. But we would have 3 here, 1 hydrogen there, and 3 hydrogens there. So let's say we have 1,4-dichlorobutene. Okay, so double bond, 4 carbons, 1, 2, 3, 4. The 1 tells us where that double bond is, so it's after the first carbon. We're going to have 2 chlorines. One's going to come off of the first carbon, and one's going to come off of the 4th carbon. So we'll have a chlorine here, and then 1, 2, 3, 4. We'd have a chlorine here.